The National Electrical Code does not specify a minimum height for installing an overcurrent device. However, the panelboard manufacturer may have specific installation instructions for their equipment. It is crucial to consult the manufacturer's documentation for any minimum height requirements. When installing a panel outdoors, the enclosure must be weatherproof. This means it is designed to protect the panel from rain, snow, ice, dust, and other environmental conditions. Use weatherproof conduit fittings approved for outdoor use. These fittings should prevent moisture from entering the enclosure. Seal the conduit entrance to the enclosure using a weatherproof sealing compound or gasket. Ensure that the panelboard is properly grounded. This includes grounding the enclosure and all the equipment inside. Ensure that the panelboard is accessible for inspection and maintenance. This may require providing a weatherproof access door or cover. If the panelboard is located under the bar, ensure that it has adequate ventilation to prevent overheating. Consider installing a lock or latch on the panelboard door to prevent unauthorized access. Provide adequate lighting in the area where the panelboard is located. Mark the panelboard clearly with its purpose and location. Keep a record of the panelboard's installation location, enclosure type, and any special precautions taken. The maximum height for installing an overcurrent device, according to Section 240.24 of the National Electrical Code, is 6 feet 7 inches to the center of the handle. When installing a panel outdoors in a wet or damp location, as permitted by Section 408.37, ensure compliance with Section 312.2 (a), which mandates the use of a weatherproof enclosure and proper conduit fittings. Several important considerations should be addressed to ensure a safe and compliant installation. Firstly, the enclosure itself must be rated for outdoor use and designed to protect the electrical components from the elements, including rain, snow, ice, and dust. Secondly, all conduit fittings used to connect conduits to the panelboard must be weatherproof and properly sealed to prevent moisture from entering the enclosure. Thirdly, grounding is critical. Ensure the panelboard is properly grounded according to NEC Article 250, which typically involves connecting the panelboard's grounding busbar to a grounding electrode system. Fourthly, accessibility is crucial. The panelboard should be readily accessible for maintenance and inspection, complying with Section 110.26 of the NEC. Fifthly, if the panelboard is installed under the bar, ventilation must be considered to prevent overheating, which could lead to equipment failure or even a fire hazard. Consider installing vents or fans to ensure adequate airflow around the panelboard. Sixthly, security is a concern, especially in a public area. Consider installing a lockable enclosure to prevent unauthorized access to the panelboard. Seventhly, adequate lighting should be provided in the vicinity of the panelboard to facilitate maintenance and troubleshooting. Eighthly, proper labeling is essential. Clearly label all circuits and components within the panelboard for easy identification. Ninthly, maintain thorough records of the installation, including the panelboard's location, circuit directory, and any specific installation details. Tenthly, consult with local electrical inspectors to ensure compliance with all applicable codes and regulations. Remember to follow all manufacturers' instructions for the panelboard and related equipment. Regular inspections and maintenance are crucial to ensure the continued safe and reliable operation of the electrical system. Proper selection of conductors is vital for the safe and efficient operation of any electrical system. The National Electrical Code, specifically Article 310, provides detailed guidelines for determining the ampacity or current carrying capacity of conductors. Several factors influence the appropriate conductor size for a given application. Firstly, the load current is the primary determinant. The conductor must be capable of carrying the continuous load current without exceeding its temperature rating. Secondly, the ambient temperature affects the conductor's ability to dissipate heat. Higher ambient temperatures reduce the conductor's ampacity, requiring the use of temperature correction factors as specified in NEC Table 310.15. D1. Thirdly, the number of current carrying conductors in a raceway or cable also impacts ampacity. When multiple conductors are bundled together, their ability to dissipate heat is reduced, necessitating the application of adjustment factors as detailed in NEC Table 310.15. (8.3). Fourthly, the conductor's insulation type plays a significant role. Different insulation materials have different temperature ratings, which directly affect the conductor's ampacity. NEC Table 310.15, the 16 and Table 310.15. The 17 provide ampacity values for various conductor types based on their insulation temperature rating. Fifthly, the termination temperature rating of the connected equipment must be considered. Conductors must be sized so that the ampacity of the conductor, after all adjustments and corrections, is not greater than the termination temperature rating of the equipment. This ensures that the equipment terminals do not overheat. Sixthly, voltage drop is an important factor, especially for long circuit runs. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. To calculate voltage drop, use the formula voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current constant, approximately 12.9 ohms circular mils per foot for copper, I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils area of the conductor. Seventhly, conductor material, copper or aluminum, influences the conductor size. Copper has a higher conductivity than aluminum, meaning that for the same ampacity, an aluminum conductor will need to be larger than a copper conductor. Eighthly, the type of raceway or cable used affects heat dissipation. Conductors in enclosed raceways, such as conduits, will generally have a lower ampacity than conductors in open-air installations. Ninthly, directing factors may apply for specific applications, such as conductors exposed to direct sunlight or installed in underground duct. Tenthly, local codes and regulations may impose additional requirements or restrictions on conductor sizing. Always consult with local electrical inspectors to ensure compliance. The NEC provides numerous tables and examples to aid in conductor sizing calculations. It is essential to carefully review these resources and apply the appropriate correction and adjustment factors to determine the correct conductor size for each application. Remember that undersized conductors can overheat, leading to insulation failure, equipment damage, and even fires. Oversized conductors, while safer, can be more expensive and difficult to install. Proper conductor sizing is a critical aspect of electrical safety and performance. The overcurrent protection device, such as a circuit breaker or fuse, is designed to protect the conductors and equipment from overloads and short circuits. The selection of the appropriate overcurrent protection device is crucial for ensuring the safety and reliability of the electrical system. Firstly, the ampacity of the conductor being protected is a primary consideration. The overcurrent protection device should have a trip rating that is no greater than the ampacity of the conductor. This prevents the conductor from being subjected to currents that exceed its safe operating limit. Secondly, the type of load being served influences the choice of overcurrent protection device. Different types of loads, such as resistive, inductive, and capacitive loads, have different current characteristics and require different types of overcurrent protection. Thirdly, the interrupting rating of the overcurrent protection device must be sufficient to handle the available fault current at the point of installation. The interrupting rating is the maximum short-circuit current that the device can safely interrupt without failing. Fourthly, the voltage rating of the overcurrent protection device must be equal to or greater than the system voltage. Using a device with an insufficient voltage rating can result in equipment failure or hazardous conditions. Fifthly, coordination between overcurrent protection devices is essential to ensure selective tripping. Selective tripping means that only the overcurrent device closest to the fault should trip, minimizing the impact on the rest of the electrical system. Sixthly, the ambient temperature in which the overcurrent protection device is installed can affect its performance. High ambient temperatures can reduce the device's trip rating, requiring the use of temperature correction factors. Seventhly, the National Electrical Code provides detailed requirements for overcurrent protection in Article 240. This article specifies the types of overcurrent protection devices that are permitted for various applications, as well as the rules for sizing and installing them. Eighthly, the manufacturer's instructions for the overcurrent protection device should be followed carefully. These instructions provide valuable information about the device's operation, installation, and maintenance. Ninthly, regular testing and maintenance of overcurrent protection devices are essential to ensure their continued reliability. Testing should be performed by qualified personnel using appropriate equipment. Tenthly, local codes and regulations may impose additional requirements or restrictions on overcurrent protection. Always consult with local electrical inspectors to ensure compliance. Overcurrent protection devices are available in a variety of types, including circuit breakers, fuses, and ground fault circuit interrupters. Circuit breakers are reusable devices that trip when an overcurrent occurs, while fuses are single-use devices that must be replaced after they blow. Ground fault circuit interrupters are designed to protect against ground faults, which can be particularly dangerous. The selection of the appropriate overcurrent protection device depends on the specific application and the requirements of the National Electrical Code. It is essential to carefully consider all of the factors discussed above to ensure that the electrical system is properly protected. Remember that improper overcurrent protection can lead to equipment damage, electrical fires, and even personal injury. Proper grounding is a cornerstone of electrical safety, providing a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protection devices. The National Electrical Code, specifically Article 250, outlines the requirements for grounding and bonding electrical systems. Firstly, the grounding electrode system is the foundation of the grounding system. It consists of one or more grounding electrodes that are connected to the earth. Common grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, often referred to as UFOs. Secondly, the grounding electrode conductor connects the grounding electrode system to the equipment grounding busbar in the service equipment. This conductor must be sized according to NEC Table 250.6C6, based on the size of the service entrance conductors. Thirdly, the equipment grounding conductor provides a path for fault current to return to the source from non-current carrying metal parts of equipment, such as enclosures, raceways, and motor frames. The equipment grounding conductor must be sized according to NEC Table 250.122, based on the rating of the overcurrent protection device protecting the circuit. Fourthly, bonding is the process of connecting all non-current carrying metal parts together to create a low impedance path for fault current. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of electric shock. Fifthly, the main bonding jumper connects the grounded conductor to the equipment grounding busbar in the service equipment. This jumper provides the primary path for fault current to return to the source. Sixthly, the supply side bonding jumper is used to bond metal raceways and enclosures on the supply side of the service equipment. This jumper ensures that these metal parts are effectively grounded. Seventhly, the load side bonding jumper is used to bond metal raceways and enclosures on the load side of the service equipment. This jumper ensures that these metal parts are effectively grounded. Eighthly, separately derived systems, such as generators and transformers, require their own grounding electrode system and bonding connections. The grounding electrode system for a separately derived system must comply with the requirements of NEC Article 250. Ninthly, ground fault circuit interrupters are designed to protect against ground faults, which can be particularly dangerous. A ground fault occurs when current leaks from a circuit to ground, such as when a person comes into contact with a live wire and a grounded object. Tenthly, regular inspection and testing of the grounding system are essential to ensure its continued effectiveness. Testing should be performed by qualified personnel using appropriate equipment. Improper grounding can lead to electric shock, equipment damage, and even electrical fires. Proper grounding is a critical aspect of electrical safety and should never be overlooked. All electrical work should be performed by qualified and licensed electricians who are familiar with the National Electrical Code and local codes and regulations. The National Electrical Code, abbreviated NEC, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their building codes. The NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, equipment installation, and special occupancies. It is organized into chapters, articles, and sections, each addressing a specific aspect of electrical safety. The NEC is intended to protect people and property from electrical hazards. It provides minimum requirements for electrical installations, but it is not a design manual. Electrical designers and installers must use their professional judgment to ensure that electrical systems are safe and reliable. The NEC is constantly evolving to keep pace with new technologies and changing safety standards. Each new edition of the NEC includes revisions and additions to address emerging electrical issues. The NEC is an essential resource for anyone involved in the electrical industry, including electricians, engineers, inspectors, and contractors. It provides a comprehensive set of rules and guidelines for ensuring electrical safety. The NEC is not intended to be a substitute for proper training and experience. Electrical work should only be performed by qualified and licensed individuals. The NEC is a complex and technical document that requires careful study and understanding. It is important to stay up to date with the latest edition of the NEC and to consult with qualified professionals when necessary. The NEC is a living document that is constantly being revised and updated to reflect the latest advancements in electrical technology and safety practices. It is essential to stay informed about these changes to ensure compliance with the latest requirements. The NEC is a valuable resource for promoting electrical safety and preventing electrical hazards. By following the guidelines and requirements of the NEC, we can create safer electrical environments for ourselves and others. Remember that the NEC is a minimum standard. In some cases, it may be necessary to exceed the requirements of the NEC to ensure adequate safety and reliability. Always exercise caution and use good judgment when working with electricity. Electricity is a powerful force that can be dangerous if not handled properly. Always follow safe work practices and take appropriate precautions to prevent electrical accidents. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with qualified professionals for specific electrical design and installation needs.